Cambridge Computer Science, Chapter 1, Data Representation, Part 3, Hexadecimal System. We did a lot of effort studying the binary system. Why do we have to study the binary number system? Because computers work in binary. Computers inside only have ones and zeros. Okay, so we call this binary because it is base 2. So denary is base 10. And this is what we have been doing all over our life. Binary is base 2. And we need to study binary because you are doing computer science. However, hexadecimal here is base 16. Why do we even need to study this? Base 16, hexadecimal, is very closely related to binary base 2. There is a very good relationship. It is very easy to represent a binary number in hexadecimal. I will show you this relationship, and we will be doing all these conversions in a very easy way. Because computers have ones and zeros, and I need to deal with ones and zeros, but ones and zeros are really lengthy and they cause confusion. So I have a very good method of converting any binary number easily into a hexadecimal number. Okay, it will be like every 4 bits in binary will be grouped and converted into 1 digit in hexadecimal. So instead of dealing with lengthy strings of ones and zeros, hexadecimal will be a shorter and a very easy way of representing binary. So we study hexadecimal because of its relationship with binary. Okay? So let us go through the basis of hexadecimal. Let us go through the basis of base 16. And then we study all the... Definitely conversion between hexadecimal and binary is very easy. However, conversion between hexadecimal and denary is more complicated. And unfortunately, you have to do all. Okay, let us go through it bit by bit and study the basis of that base 16 numbering system. And then we solve and practice as much as required. Okay. Hexadecimal system. The hexadecimal system is very closely related to the binary system. That's why we need to study the hexadecimal. Hexadecimal is referred to as simply hex. Okay? Sometimes they call it hex. Okay? We don't need that piece of paper. Hexadecimal is a base 16 system. Hexadecimal is a base 16 system. Okay? Let us study the mathematics of base 16. When you have a number that is base 16, you need 16 figures. 0 to 9, we have them. We have the figures 0 to 9, but this is only 10. We also have other figures, that is A, B, C, D, E, F. So in hexadecimal, 0 is a 0, 1 is a 1, 9 is a 9. However, A is 10, B is 11. And please, you try to memorize them. Until you memorize them, when you are doing an exercise, you just write 10, 11, A, B, C, D, E, F. Beside it, 10, 11, 12, 13, 14, 15. You end with F, that is 15. We need that. We need that definitely. Okay? Because a number in hexadecimal would be 5A. What is that 5A? The 5 is 5 and the A is 10. Why do I have to go that far? Because I need 16 shapes. 0 to 9 are the same, and then A, B, C, D, E, F, it is equivalent to 10, 11, 12, 13, up to 15. Okay? Okay. That's why the numbers 0 to 9 and letters A to F are used to represent each hexadecimal digit. Okay? A is equal to 10, B, C, D, E, and F is equal to 50. Okay, that's about a number that is being base 16. What else? When a number is base 16, column headings are powers of 16. So column headings are 16 to the power of 0. Anything to the power of 0 is next 16 to the power of 1, that is 16. Next 16 to the power of 2, that is 256. Next 16 to the power of 3, 16 to the power of 4. I don't think we will be dealing with that big complex numbers. Okay, so please, for the moment, memorize that column headings are 1, 16, 256. This is 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, and the rest don't memorize. No need to memorize. I don't think they will show in the exam because that would be too complex and you are not allowed to use calculators. Okay? And the good thing is that since 2 to the power of 16, since 2 to the power of 4, since 2 to the power of 4 is equal to 16, this means that 4 binary digits are equivalent to 1 hexadecimal digit. We will be using that all over. Okay? Okay. Sometimes students memorize that. You will not memorize. You will get used to it very, very soon. Because every 4 bits in the binary will convert into 1 hexa. So 0, 0, 0, 0 will convert to 0. 0, 0. The weights are, because weights are really simple. They are 1, 2, 4, 8. And if the number is bigger, for example, 8 bits, you group them into 2 groups of 4. And the weights remain 1, 2, 4, 8. For example, this is 3, and this is 3. For example, this is 4, and this is 4. So if you have here 1, 0, 1, 0, so it is 8 plus 2, that is 10. In binary, it is 10. In hexa, it is 8. Very, very soon, when you see the A, yeah, A is 10, and it converts into 1, 0, 1, 0. I even memorize it. This is exactly what is expected from you because computer engineers, they convert binary to hexadecimal just by looking. Okay? Okay. So F is 4 ones because 1 plus 2 plus 4 plus 8 is 15. And 15 is F. Okay, now we are halfway through studying conversion from binary to hexa or hexa to binary. This is supposed to be very easy, no matter how long the number is. Okay, so let us go through examples and you work out things by hand. And this is equivalent to solving past papers because all these questions are just copied from past papers. Converting from binary to hexadecimal is very easy. Converting from binary to hexadecimal is very easy. Starting from the right and moving left, split the binary number into groups of 4. Why do I need to start from the right? Because if they are not multiples of 4, you may fill zeros on the left. Zeros on the left are insignificant. Okay? Okay. If the last group has less than 4 bits, then simply fill in zeros from the left. Zeros on the left are insignificant. Recording. Okay, so if you don't have enough digits, enough bits to make them groups of 4, just fill bits on the left because 1 zeros on the left. Okay, take each group of 4 bits and convert it into the equivalent hexadecimal using the table or using weights. Let us do weights until you can memorize the table above. Okay? Okay, let us have an example. You have a number that is 1 0 1 1 1 1 1 0 0 0 0 1, and there will be no coloring in the exam. I am the one who is coloring bits in blue. Okay, so if you'd like to convert this into hexadecimal, you proceed as follows. Starting from the right, make them groups of 4 bits. So this is a group of 4 bits. This is a group of 4 bits. This is a group of 4 bits. And for the moment, until you can memorize this table, put weights. And the beauty here is that weights are 1, 2, 4, 8. And then you start all over again. 1, 2, 4, 8. 1, 2, 4, 8. You don't have to go to 16, 32, 64, and that big numbers. Okay? This is what makes converting from binary to hexa an easy task. You convert every group on its own. Okay? So here, this is 0, 0, 0, 1. This is 0, 0, 0, 1. You put weights 1, 2, 4, 8, and this is just 1. So 1 is 1. Okay? And here, that group 1, 1, 1, 0, you put weights. That is 1, 2, 4, 8. You have 8 plus 4 plus 2, and that is 14. However, 14 is E. Again, the last group is 1, 0, 1, 1. You put weights 1, 2, 4, 8, and that is 8 plus 2 plus 1, that is 11, and 11 is B. So the equivalent is BE1. Okay? And now we are done converting. Okay? Very easy. Okay, so it is very easy, no matter how many bits. So even if you are dealing with 16 bits, I don't mind. Okay, so the following 16-bit machine code instruction is stored in a location of memory, of main memory. 1, 1, 1, 0, 1, whatever. We would like to convert this into hexadecimal. Please go ahead and convert that yourself. You split them into groups of 4. Here I have them split into groups of 4. And convert each group individually. 16 will convert into equal 4 groups of 4. You don't need to fill with zeros. So these individual groups convert to that group here 0, 1, 1, 1 is 7. That group here 1, 0, 0, 1, so it is 8 plus 1, and it is 9. This group here 1, 0, 1, 0, so it is 8 plus 2, this is 10, and 10 is 8. This group here 1, 1, 1, 1, this is 15, and 15 is F. Okay, another example. And actually, all these examples are taken from O-level exams. Okay, convert that pattern again to hexadecimal. So again, so easy. So this is 1, 1, 1, 0. This is 8 plus 4, 12 plus 2, 14, and 14 is E. This is 1, 0, 1, 0. Now I can recall that 1, 0, 1, 0 is 8. 1, 0, 1, 0 is 8 plus 2. It is 10, and 10 is 8. And this 1, 0, 0, 1, and this is 9. because it is 8 plus 1. And this is 0, 0, 0, 0, and this is 0. Okay, now we have a little challenge. They are giving you 10 bits, and 10 is not a multiple of 4. You need to have a multiple of 4 to be divided into groups of 4. Okay, very easy. Fill zeros on the left. Okay, so if you have 10 bits, filling zeros on the left. Okay, please work on that. So first we start by filling zeros on the left, because 10 is not a multiple of 4. You may only fill zeros on the left, then they are insignificant. And then you group these 0, 1, 0, 1 in here, and this is 5. And then you group this. This is 1, 0, 1, 1, and this is B, 11B. And this 1, 0 goes here and added 2 zeros, and this is just 2, so it becomes 2, 8, 2B, 5. Okay? Excellent. That was so easy. Converting from hexadecimal to binary is just the same. Every single hexadecimal digit will be converted into 4 bits binary. So if you have, for example, 0C, the C0 will be 0, 0, 0, 0. The C is 12. It will be 1, 1, 0, 0. Okay, again, do that yourself. Convert the following hexadecimal number into 12 bits binary. 4AF. The 4 is 4 bits, the A 4 bits, and the F 4 bits. Please fill the pattern and check with me. You are expected to do that orally. So 4 is 0, 1, 0, 0. A is 10 and it is 1, 0, 1, 0 because it's 8 plus 2. And F is the last digit. F is 15. And also I know that 15 is 4 ones because it is 1 plus 2 plus 4 plus 8. Okay? Okay, that was easy. Let us go to the more difficult job. Converting hexadecimal to denary. The point is, we now need to recall weights. Hexadecimal is base 16. Okay, so if you have a number in hexadecimal and you want to find the denary equivalent, you just put weights that are 1, 16, 256. Hopefully, there will be no more than 256. 1 is 16 to the power of 0, 16 is 16 to the power of 1, 256 is 16 squared. Maybe now you need to remember the multiplication table of 16. Okay? Okay. To convert this hexadecimal number to denary for FA, I will do that myself and I will leave you to verify it afterwards because numbers here are really big and complex. That example has never been in an exam. That big number has never been in an exam. I'm just copying this from the textbook. Okay, let us have a look at that. So you have 4FA. You put weights. 16 to the power of 0, 16 to the power of 1, 16 to the power of 2. And these are 1, 16, 256. And then you put the 4FA. The 4 is 4. So 4 multiplied by 256. The 5 is 5. So 5 multiplied by 16. However, the A is 10 and A multiplied by 1. And then this multiplication, you have 1024. This multiplication results in 80. 8, 10, 10 by 1 is just 10. You add them together, 1024 plus 80 plus 10. That becomes 1140. Okay? Please work on these because these are just 2 digits. I can do that orally. I can do let me go through these very simple examples orally, and then allow you time to work out more realistic example. But these were in exams. They give you just 2a, and that number is in hexadecimal, and the a is 10. The 2 is 2 and the a is 10. Okay, you put weights 116 above the 2 and a. Okay, so 16 by 2 is 32 plus a 10 multiplied by 1, so it is 32 plus 10, and it is just 14. Okay, again, let me go through all these very simple examples myself and leave you with more realistic examples. Okay, another example, 101. Weights are 116, 256. So it is 256 plus 1, so it is 257. Easy? Okay, sometimes they give you beautiful numbers. They go together because the exam is about the concept and there is no calculator, so they have to take it easy on you. Okay, next, 21e. Okay, you do that first. Put weights 116, 256. The E is 14 because the F is the last one, that is 15. The E is 14. Please give yourself time. So you have 2 below the 256. Twice 256 is 512. You have 1 below 16. You have E, that is 4 below the 1. So it is 256 plus 16 plus 14. So it is 500, I'm sorry, 512 plus 16 plus 14. So it is 514. Okay? Let us go to the most difficult. Not very difficult. It's not that difficult. However, instead, now we want to study how to go from denary to hexa. The point is, from hexa to denary, you multiply by 16. When you do the opposite, denary to hexa, you will be dividing by 16 and finding the remainder. Okay, that's why it will be very helpful. For example, just memorize that 5 by 16 is 80. Just memorize the multiplication table of the 16, because hexadecimal is base 16, so it is all about multiplying or dividing by 16. When it comes to conversion between hexadecimal and denary, hexadecimal and binary is very, very, very easy. Okay, and that is even why they invented the hexadecimal. Okay, to convert from denary to hexa is a little bit more difficult. Okay, there are 2 methods. The method is trial, and the second method is involve repetitive division by 16 and finding the remainder. I will always use the trial method. Okay, we try to figure out where to put ones in appropriate. No, it's not about ones, about putting values in appropriate places. Okay. So if you have consider this example is really difficult. I will go through it just for clarification, and I will give you simpler examples. So we would like to convert 2004 into hexadecimal. You need to place here, for example, 7, and here D, and here 1. This is so complex. The point is 2004 divided by 256, you get 7, remainder 12. You put the 7 here. On the 212, we put 7 under here. And the 256 We put 7 under the 256. Okay. Okay. And the remainder is 212. 212 divided by 16 equal 13, remainder 4. Okay, so the 13 goes here as D. Okay, and the 4 goes here as 4. We put D instead of 13 under the 16. We put the remainder 4, that is 4. We put the remainder 4 under the 1. Which method show that 7 multiplied by 256, 13 by 16, 4 will give 2004. Okay? Okay. We also have, this is the trial method that I will be using. However, in realistic exams, they don't go that far. Okay? There is what is called repetitive division method. You divide by 16 and find the remainder. You divide by 16 and take digits 7, 13, 4. You write it at 7D4. Okay, okay. Let's not go so much into that. Let us do easier things. Let us, because that was the theoretical background. Just leave it aside. Let us go to practical. Let us consider this. Find the hexadecimal value obtained when two hexadecimal digits C and D are added together. I have C, and C is 12, plus D, and D is 13. 12 in denary plus 13 in denary is 25 in denary. However, I would like to know what is the hexadecimal equivalent of that 20. Okay? Okay? So now we need to convert 25 into hexadecimal. It is very easy because you have such a small number. Weights are 256, 16, and 1. Definitely, you put a 0 under the 256, or just ignore it. And then, let me do that in front of you. Let me do that in front of you. I can draw. It is like this. You have 25. Okay? You have 25. Divide that 25 by 16. Okay? How many times the 25 goes into 16? This is just 1. 1 multiplied by 16 is 16 here. And when you subtract, the remainder is 9. It is very simple. That quotient, put it here. And that remainder, put it here. And that's it. So 25 in denary becomes 19 in hexadecimal. Okay? So when you have 2 digits, just divide by 16 and find the remainder. And if you go to the example above, it will be the same concept, but however, at that time there were 3 digits. Okay? I think you will only be dealing with small numbers. Okay? So now I have successfully converted 25 into hexa by dividing by 16 and finding the remainder. Okay? Okay. Can you do the same? Let me get rid of that draw. Can you do the same converting 179 in denary into hexadecimal? Okay, I will hide this because this is the answer. Okay, your duty now is divide 179 by 16. Find the quotient and the remainder. Okay, and you need to practice how to do long division. Okay, you are supposed to do a long division like this. 179 divided by 16. 17 divided by 16, you have 1. 1 multiplied by 16, you get 16. Subtract, and the remainder is 1. You pull down the 9, you have 19 divided by 16, again 1. 1 by 16, subtract, the remainder, 1 by 16 is 16, 19 minus 16 is remainder 3. So the 3 goes into here. The 11 goes as B under the column 60. And that's it. And if you do the opposite, you multiply and add, you get 117. Okay? Okay, please. Now do 251. We would like to convert 251 into hexadecimal. Okay, divide by 16, log division, find the quotient and the remainder. So 251 divided by 16, the result of division is 15, remainder 11. The 15 becomes F, remainder 11, the 11 becomes B. So you have FB, and then this is the representation of 251 in hexa. Okay, we have plenty of examples. We have plenty of examples. I will go through this, and you please redo that yourself, because it will take us a lot of time. Actually, all these are copied from the classified. So I will just discuss these with you to finish the session and discuss the rest of what I want to say. And then you have to work all these yourself. So in that question, this is binary or hexadecimal. You can easily figure out whether this is binary or hexadecimal. Okay, so this is binary. You put weights 1, 2, 4, 8, 16, 32, 64. When you add, it will count, it will result in 57. So you leave. Okay, 4E is in hexadecimal. You put 1 and 16, and E is 14. Okay, 16 by 4 plus 14, 78. Okay, you put here what weights 1, 2, 4, 8, and so on. You put here, and A7 is hexadecimal. You put 1 and 16. 16 by 10, and the A is 10. 16 by 10 is 160 plus 7. This is 167. So some easy numbers are shown. 19. 19, you put weights 1 and 16. So 16 plus 9, and that is 25. We spent some time converting the 25 denary back into hexa. That was 90. Okay? You have to be able to do this. So please do this in your classified. What other examples? Let me discuss those examples with you. Let me go a little bit further, because so in here, this is a screenshot of the marks. What was the question in the first place? You were given those values in hexadecimal. 0 to 8. If you'd like to convert 0 to 8 into binary, the 0 goes into 4 zeros. The 2 goes into 0, 0, 1, 0. And the 8 goes into 1, 0, 0, 0. Now it's up to you. If you want to find the denary, you may start from hexa, putting 116. 16 by 2 is 32 plus 8, and this is 40. Or you may put here 1, 2, 4, 8, 16, 32. Again, you will find that it is 32 plus 8, and that is 40. So if you are accurate, you may convert from here to there, and it's going to be the same. Go and play with numbers until you are really confident with hexadecimal, binary, and denary. The three together, because you will be asked to convert between any of the three. Okay, again, 1A9, So the 1 goes here as 0001. The A is 10 and it is 1010. The 9 is 1001 because it is 8 plus 1. And it is up to you to put here 116, 256, multiply and add to get to that. See, questions now are getting more challenging. These are the most recent questions. Earlier questions were taken from all the exams. I always train you with easier ones, and then we get to the real ones. Okay? 206, the 2 is 0010, the 0 is 4 zeros, the C is 12, and it is 8 plus 4. Okay? You can find the details of all this here. Even how to do addition. 256 plus 160 plus 9. You can go through this. Okay? These are all copied from past paper, classified. I think it will be among your homework. Okay? Another example. Here you are starting with 49 denarii. So from denarii to hexa, you need to divide by 16 and find remainder. 49 divided by 16, I can just say it's going to be 3 remainder 1. It will be very easy if you memorize the multiplication table of 16. So 16, 32, and then 48, okay, and so on, because calculators are not allowed. 132 divided by 16, this is 7, remainder 11, and 11 is B. 200 divided by 16, 12, remainder 8, and 12 is C. And afterwards, if you like to convert from hexa to binary, it's going to be very easy. 3 is 0011. 1 is 0001. Okay. 7 is 0, 3 ones. B is 11. That is 1011. C is 12. That is 1100. 8 is 1000. Another example. Another example, you have to go through all these in your classified exercise. I think, and let me figure out what was the question and what was the answer. I think they gave you this and that and asking for the hexa. If you have the denarii and binary and would like the hexa, it would be easier to work on the binary and find the hexa. Things in bold are the answer. Okay, so they give you that and that, and you like the hexa, it is easier from binary to hex because 0001 will be 1 and 4 ones is it? Is 50. Okay, they give you that and that, and we like the binary. Okay, hexa to binary is easy. So 8 is 1000 and C is 12, that is 1 and 1 and 00, 12 is 1, is 8 plus 4. Okay, they give you that and want this. Okay, put weights 1, 2, 4, 8. So put weights 1, 2, 4, 8, 16 and add this 90, or put here weights 1, 16, multiply and add, and it's gonna be 90. Remember that 5 by 16 is 80, plus A, that is 10, is 90. Okay, okay. The last thing to say, again, why do we need to use hexadecimal in binary, in computer science? Why do we need to use hexadecimal in computer science? We know for sure that we must use binary in computers because computers are all binary. Why do we need to study hexadecimal? Okay. Uses of hexadecimal numbers in computer science. The MAC address, everything, all the examples I will say here will be such that they are actually in binary inside computer, but it would be easier to represent for human in hex. So the MAC address is actually ones and zeros inside of the computer, but it would be easier to represent it for humans as hexadecimal because they are shorter and they are easy to convert back and forth between binary and hex. Okay, color codes in HTML. This is ICT. Okay, are in hexa. Remember FF0000 that used to represent the red. Okay, just here they are just an example. Error messages, they are in binary and they are rather represented for humans in hexa. Locations in memory, memory dumps, IP version 6. IP version 6 is represented in hexa. ASCII code and Unicode, we will be studying this next session, inshallah. Assembly language, all these are just example of data inside of the computer that are in the form of ones and zeros. Truly and really, they are ones and zeros. However, for easiness, they are represented for humans in the form of hexa. Okay, and that was an answer to an exam. They ask you why example use of hexadecimal. And they also may ask you what are the benefits of using hexadecimal numbers in computer science. Hexadecimal can represent 4 bits as only one hexadecimal. Then fewer digits are used and so take up less space. Hexadecimal is easier for humans to understand than binary, easier to identify values and spot errors, faster than binary for entering, easier and quicker to read and understand, and after all, it is easy to convert hexadecimal digits back to binary if necessary. Okay, I will stop here. That session was very important about all what you need to know about hexadecimal. Okay, please practice a lot because computer scientists they use hexadecimal in a very, very comfortable way. Okay, and you are prepared to be a computer scientist or a computer engineer because you are studying computers. Okay, I hope everything is clear. Thank you very much for understanding.